Hello and welcome. In this video, we are going to learn about the overall imperfection method. We are going to take an overview of the theoretical background, then we will look at application examples in Consteel. Let's get started with the theory. The overall imperfection method is one way to carry out the buckling design for a structural member. Based on the fundamental approach, where we compare the effects and resistances of a member, there are two different ways to account for the buckling effect. The more usual way is the strength reduction method, where we consider the buckling effect through a reduction of the cross-sectional resistance. This reduction is introduced with the help of a strength reduction factor on the resistance side of the equation. On the other hand, we can also use the imperfection method, where the buckling effect is considered through a properly scaled imperfection shape. In this case, we add an additional second-order load effect to the effect side of the equation. In both cases, there are several calculation schemes available. Within the strength reduction method, we can do member checks or use the general method. In case of the imperfection method, the aim is to figure out what kind of additional load effects we need to add and how should we scale those, from which the scaling is the harder question. There are two options available in the Eurocode to get the scaling for the imperfection. The first one is the equivalent initial bow imperfection, which works with simple formulas and usually gives a quite conservative estimation. The second one is the equivalent imperfection, where a more advanced formula is available, which accurately approximates the scaling, but still only applicable for flexural buckling and a very limited range of structural properties. The third and new option within this category is the overall imperfection method. This method aims to more precisely consider all kinds of stability phenomena and to be applicable to a wider range of structural properties, namely non-uniform internal force distribution, eccentric loading, varying cross-section size, and arbitrary boundary conditions. The overall imperfection method uses a buckling shape as an imperfection, scaled in a way that its effect is the same as if we were using the strength reduction method. If we insert the buckling resistance into the equation of the imperfection method, we can see that there is a straightforward relationship between the reduction factor and the second-order load effects. The key of the overall imperfection method is to find the appropriate scaling factor for the chosen buckling shape to have the equal effect as the standardized strength reduction method. To figure out the proper scaling factor, we need to carry out a multiple-step calculation process. First, we need a linear static analysis to get the internal forces and moments, and also a linear buckling analysis to get the buckling shape and the critical load multiplier. To be able to apply the strength reduction-based standardized calculation formulas of the Eurocode, we need to substitute the real member with a so-called equivalent reference member. This reference member has to have a prismatic cross-section, has to be simply supported, and its internal forces need to have a uniform distribution. The approach of the equivalent reference member works similarly to the effective length concept. The same way the effective length helps us to apply the well-known calculation formulas of the fundamental case of the flexural buckling to a wider range of possible support conditions, the equivalent reference member helps us to do the same in a more general sense. Let's say we want to examine this member with varying cross-section and load effect. First, we need to determine an equivalent point along the lengths where we want the buckling deformation to be the same on the real and on the equivalent reference member. For this, we need to calculate the load effects that would result the buckling shape, which are called the modal internal moments, and compare it to the cross-sectional resistances. The equivalent point will be chosen to be the point where we have the maximal cross-sectional utilization for the modal internal moments. The normalized version of this utilization is called the imperfection sensitivity in Consteel. The equivalent reference member will have the same cross-section and internal forces along the whole length that the real member has at the equivalent point. In the standard, there are several different ways to calculate the reduction factor depending on what kind of stability phenomena we are dealing with. To be able to use the correct calculation method, we have to classify our specific case into one of these categories. For example, in case of doubly symmetric cross-sections, there are 5 applicable buckling mode classes, which are the following: strong axis flexural buckling, weak axis flexural buckling, torsional buckling, lateral torsional buckling, and coupled lateral torsional buckling. The buckling mode class is chosen based on the load effect and the buckling mode shape components at the equivalent point. The last thing we need to define for the equivalent reference member is the equivalent length. Knowing the cross-section and the load effect of the reference member, we have to figure out an equivalent length that will ensure the same buckling deformation at the equivalent point. The equivalent length is calculated based on the equation of the elastic critical load for the selected buckling mode on the real member and the analytical formula for the critical buckling load on the equivalent reference member according to the determined buckling mode class. If we get back to the effective length analogy, the comparable version of the equivalent reference member would be the scaled version of the fundamental pinned-pinned buckling case. However, with the overall imperfection method, we need to consider more parameters to ensure the equivalence than just the length. Now that we have all the parameters for the reference member, the equivalent imperfection factor can be calculated based on Eurocode formulas. In the next step, we need to calculate the amplitude scale factor for the buckling shape to get the equivalent geometrical imperfection. The amplitude scale factor can be calculated from the following equation. The equation states that the cross-section utilization for the modal internal forces derived from the real buckling mode shape on the real member at the equivalent point is equal to the cross-section utilization for the modal internal forces derived from the standardized sinusoidal buckling mode shape on the equivalent reference member at the middle. From this equation, the amplitude scale factor can be expressed. It is important to point out here that the amplitude scale factor is calculated based on the standardized, calibrated value of the equivalent imperfection factor. This is how it is ensured that we will have the same effect using an imperfection to account for the buckling phenomena as if we were using the standardized strength reduction method. As a last step, the buckling design is carried out by running a second-order static analysis on the real member with the equivalent geometrical imperfection, and then performing a simple cross-section check with the help of the linear conservative interaction formula. The cross-section is checked for the normal, unreduced strength, but the effect of the buckling is considered through the increase of the internal forces. In summary, the overall imperfection method performs the buckling design with the help of the second-order load effects coming from a properly scaled buckling shape. Now, let's see some examples in Consteel. We are going to go through examples with increasingly complicated properties to show the capabilities and advantages of the overall imperfection method. This first one is a simply supported prismatic beam loaded with a normal force. In the imperfection sensitivity result, we can see it is 100% in the middle, which means that will be the equivalent point. As a reference, first let's perform the design with the usual general method. The examples are set up in a way that we would get approximately 100% utilization with the general method, so we can easily compare it with other results. Notice how in this case, there are no additional internal forces within the second-order results, only the normal force. Let's now get back to the Analysis tab and apply the critical buckling shape as an imperfection. The buckling shape is a weak axis flexural buckling. At the amplitude determination dialog, there are the three previously mentioned methods to calculate the equivalent amplitude: the initial bow imperfection, the imperfection based on the elastic critical buckling shape, and the overall imperfection method. The first one would give a 20 mm amplitude. The second one a 6.7 mm amplitude. And the OIM also a 6.7 mm amplitude. In the OIM details, we can find the location of the equivalent point, the buckling mode class, the equivalent length, and the amplitude scale factor before we can get the actual amplitude for the buckling shape in millimeters. Note that it is buckling mode class 2, which means weak axis flexural buckling. Let's apply this one. If we now go back to the Loads tab and open the imperfections, we can find our imperfection case with the amplitude scale factor. Let's run another analysis, but this time with the added imperfection. Then run a cross-section check based on the second-order analysis results. We get the same 100% utilization, however this time there are additional internal forces in the second-order results. These additional forces are how we consider the buckling phenomena with the imperfection method. Note that we got the same utilization result for different internal forces, but without the reduction of the strength in this case. This is because we scaled these forces with the calculations of the overall imperfection method to have the same effect. One advantage of this approach is that we can specifically see what forces represent the buckling effect, and we can also see the difference compared to the first-order results where these forces are not present. In the second-order analysis result, we can check out these internal forces for the entire member. Also, if we look at the deformation, the second-order results contain the buckling deformation, while the first-order results do not. Alright, now let's check out the same member, but with a uniform bending moment distribution. The general method result is again 100%. Let's now apply the imperfection. Note that in the OIM details, now there is not only MZ modal force, but bi-moment as well. Also, it is buckling mode class 4 now instead of 2, which means lateral torsional buckling, and in the equivalent geometric imperfection, there is not only deflection, but twist as well. Let's run it again with the imperfection, and then the design. The result now is 98%, and we can see the additional second-order internal forces. Also, if we run a member check, we get a close to 100% result as well. These were the fundamental cases. Let's add some complication to this model and have a linear moment distribution instead of a uniform one. The general method utilization is again 100%, and its maximum coincides with the maximum of the first order bending moment. Let's apply the imperfection. As we can see, the equivalent point is not in the middle in this case. This is because the buckling shape is not symmetrical, since the loading is not symmetrical. Also because the moment distribution is not a fully uniform constant distribution, but a triangular one, we have a more favorable setup compared to the fundamental case, which means that the equivalent length will be shorter than the original 5 meters. It is important to point out here that if we use the overall imperfection method, we should always choose the conservative interaction resistance in the design results. The utilization is 80% now, and the place of the maximum is not at the largest first-order forces, not at the largest modal internal forces, but actually at a point where these two effects are the largest in combination. If we perform a member check in this case, the utilization will be 87%, which is a result between the two other methods. This result is lower than the general method one because there is an F modification factor implemented here that takes into account the non-uniform moment distribution and moderates the value of the reduction factor. The overall imperfection method more precisely accounts for the actual moment distribution, that's why its result is even lower than the member check result with the modification factor. If we look at the utilization distribution along the member, we can see that the general method result is an increased version of the cross-section result, where the ratio between them is the reciprocal of the reduction factor. However, in case of the OIM, there is only additional increase in the utilization where the internal modal forces would justify it. That's why the maximum utilization is not at the maximum first-order internal forces, and we can get a more precise and more favorable result this way. In the last example, we will look at the complete warehouse building. It has all the usual load cases and a large number of load combinations. Also, there is a sway imperfection added from buckling shape 22. Let's say we already performed the design for all of the combinations and found out that everything is okay, except at combination 74 we have a slightly over 100% utilization. Let's perform the buckling design for this combination with the OIM. We need to select buckling shapes that well represent the buckling phenomena along the frames. Let's apply the first buckling shape for the middle part of the rafters. Note that in this case it is buckling mode class 5, which means coupled lateral torsional buckling. Then apply the third buckling shape for additional loads around the frame corner. After that, the additional loads from these two imperfection cases representing the buckling phenomena will be superimposed along with the sway imperfection case. Let's rerun the analysis. Then perform a cross-section check. We now have a 96% utilization at the columns, where we had over 100% previously, and we also have 77% at the middle part of the rafters, where we had 88% before. In other words, we could prove the adequacy of this structure by more precisely taking into account the complex structural properties, general boundary conditions, and internal force distributions for the buckling design. In summary, the overall imperfection method provides a more advanced, more precise, and more insightful way to carry out the buckling design. It has the capability to account for the exact, non-uniform load distribution, eccentric loading, varying cross-section size, and arbitrary boundary conditions, while its effect is fitted to the buckling curves of the Eurocode. However, it cannot be automatically calculated for several load combinations, like the general method buckling design can. For a specific load combination, it may give more favorable results and thus provide a more economic design. This concludes our introduction of the overall imperfection method in Consteel 14. Related scientific articles about the detailed theoretical background, application, and validation are listed in the video description. We hope you found this video useful. If you did, please consider liking and subscribing. Also visit consteelsoftware.com and download the trial version of Consteel for free if you are interested. Thank you for your attention.